Okay, hello again. I'd like to continue with some of the ideas that I presented yesterday. We presented a lot of material, the basics of radiation, the Planck function, some of the special features of the Planck function for short wavelengths and long wavelengths. And then we started talking about the spectral regions of the visible, near infrared, and infrared, and some of the signatures coming from clouds, from dust, from aerosols, from land, from vegetation, and from ice. Today I would like to demonstrate a few of these with some data sets over China that have been gathered by Iasi, with AIRS, and also with MODIS. Most important thing I want to tell you today is that I don't know the Chinese region very well. I know the spectral regions quite well, but when I look at the Chinese region and investigate what I see with the Earth remote sensing instruments, I need your help. And part of today then will be, I will show you some things and perhaps you can explain them to me because you know China, you have the local knowledge more than I do. The software that I'm using today, I'm giving to you on this disk, or you can also access it on an FTP site. It's very important that when you have data, that you have a visualization tool. You probably already have some visualization tools you like, so you maybe don't need this. But perhaps after I demonstrate some of the things that I do with HYDRA, you will also want to try them out. But the most important thing with our global observing system is that you can access the data locally, you can investigate it, you can try out some of the spectral information that we have shared with you or that you already have, and that you can learn together on it. Again, the idea, local knowledge with environmental remote sensing data can help us to take better care of ourselves and the planet. So, I'm going to talk about HYDRA. It's an acronym. I can't remember what the acronym stands for, but it's a visualization tool where you can look at many spectral bands. And as I said, then I will use some MODIS, AIRS, and Iasi data over the Chinese region, and we will explore it together. The most important thing with HYDRA, the hyperspectral viewer of development of research applications, is that you can access it from this website or from this disk that I gave to academician Xu Zhimin yesterday. It's on here. Also on here are several lectures that I've given in various aspects of remote sensing. And there are data sets on here, not over China, but over Europe. There are also lab exercises where you can try to do things that I encourage you to do with those data sets. There's also an article on here that explains HYDRA and how you use the various applications, buttons, if you will, the functions of HYDRA. So it's explained in such a way that you hopefully don't have to read too much material, but I'm sure that what I do today in front of you will be too fast for you to follow. So you will need some instructions. HYDRA itself has been developed by Tom Rink. He's a colleague of mine, a very bright software man. HYDRA is come about because I used to give lectures using MATLAB. And MATLAB costs money. And this was always frustrating. I would go to different parts of the world and I would give a lecture using MATLAB and demonstrate tools. And then at the end of the day I would go home with MATLAB and nobody in the country where I had just visited could afford to buy MATLAB. So I asked Tom Rink, can you build me something that's free? And he did. He built it. It's freely available software. It's at this website. I have a version called 1.88 on here. And probably in about 3 months to 6 months we'll have version 2.0. But 1.88 will still work at that time. But I encourage you to go to this website periodically, every 6 months maybe, and download the new version. Because we're adding different instruments and we're refining some of the capabilities. And users come up with suggestions on how to make it better. One of the things I will demonstrate to you today, HYDRA is not perfect. You will ask it to do too many things too fast, and it will stop. And you will have to just get out of HYDRA and get back in and start all over. So it's not perfect yet, but it's quite good. Tom Rink, Tom Whitaker, Kevin Baggett, they're my heroes here. Kevin Baggett is the one who put a lot of work into the MATLAB version, the version that costs money. So we stopped that. Tom Rink put the version together that's free. The free version is based on something called VisAD. My colleague Bill Hibbard did a lot of work on VisAD, where you're able to visualize different data sets, not just remote sensing data. And I don't know what I'm saying right now, but I'll say it anyway. It uses Jython, which is a Java implementation of Python. A few of you probably know what that means. I don't. But it's the software, it's free, and it works quite nice. For you to put it on your own computer, the requirement is for you to have a bit of memory, so 512 megabytes of main memory, and probably very important that your graphics card should be at least 32 megabytes. So, at any rate, these are sort of the minimum requirements so that so that HYDRA ends up being responsive to your commands. It's pretty fast on my little computer. You'll see that. I had a lot of help in putting together some of the requirements by my colleagues Paolo Antonelli, whom some of you perhaps met when he did a training course in Nanjing many years ago, 4 years ago, Alan Wong, whom you met the other day, and Liam Gumley. These people have had many ideas, and I've borrowed a lot of them for what I'm doing. Currently, HYDRA can look at Severi data. This is the European geostationary satellite. It can look at GOES data, or GOES imager, the 5 channels, and MODIS, AIRS, and Iasi. And also, most recently, we can compare MODIS data with Calypso data. I have no Calypso data over China, so perhaps, if I have time, will show you some comparisons of MODIS and Calypso near New Zealand in the Pacific Ocean. Only if we have time. So, very important, the address where you can get your HYDRA updates. But then also important, where would you get MODIS and AIRS data? Iasi data you have to contact UMETSAT. But MODIS and AIRS data are readily available because NASA sustains a EOS DIS website. Rapid Fire is where for the fires, but you can also access the MODIS data. So this is a website that's useful. And if you want to order MODIS data that isn't in the Rapid Fire, then you can go to something called LADS Web, nascom.nasa.gov. This address is different than the one I communicated to you several years ago. NASA has just changed in the last 6 months to a new location, and that's where you get your MODIS orders. For anything, actually, you can go to the DAC Goddard NASA Gov site, and this will direct you to LADS Web, or you can get your AIRS data from the DAC. So these are the different websites. I'll come back to this slide at the end so you can copy it down, but I'll move on. The important thing here is to get access to remote sensing data of what I think is some of the newest types with a lot of spectral bands, to look at them on your local software, and I'm offering you the HYDRA software as an example. So there is an article in BAMS, the Bulletin of the American Meteorological Society, in February of 2007, so this year, February, where it introduces HYDRA. And it also will explain to you how to use the tools, the different functions. I will also, on this disk, give you an article where it includes this article and the functions of the various tools on HYDRA. So I'm going to switch away from the prepared presentation now, and let's try HYDRA out on some Chinese data, or data over China. What you find when you click on HYDRA, as you install it, here I have run HYDRA, you click on it and you get a table here that tells you what's happening. If nothing is there, that's good. That means HYDRA is working very well. When this black table fills with comments, that means you asked it to do something that caused problems. After a while, then you have to just click on this button and start all over. But now I've gone to load some data, and in this case I went to local data, and I have some data in that what I call is the lab China. And I pulled up here the data from June 6th of 2007. So what's today? It's maybe 2 months old. And the data you recognize here then, the region, you have some clouds, you have some water, you have some land, and you have some land that's dry, and you have some land that's vegetated. When you look at HYDRA, you have various functions here. You could have tools, you could capture this display so you could put it into an article or something. You have settings where you could say, I want to see this in color. There, I have it in color. You could say, I don't like those colors, and you could change the colors by set color range, get more blues, get more reds. So you can adjust these, and what you see in the bottom is what the range is here from purple to green in terms of brightness temperature. And we're looking by default at the 11 micron image, the infrared window. So I'm going to go back to black and white because we want to make sure we know what we're doing. So this is black and white, and I'm going to set the color range so that I cover the available temperatures. And so that's settings. And now I can try out some of these buttons. This button is a magnifying glass. So I can zoom in. Well, I lost Beijing. At least I think I did. So I can pull down here, and somewhere in this region, I think Beijing occurs. Again, local knowledge. Am I in the wrong region? Perhaps you can show me.
Yes.
Right here?
Yes. Around here, is that correct?
Oh, right here.
Around here.
Very good. You're just about to have some clouds come in, possibly. So I can also go back again. And as I demonstrate, I can slide this around so that you can, as you blow things up, you can get to the region you want. I can move this around and find out exactly what latitude and longitude I'm at. And that's pretty much it. So this part of HYDRA is not that exciting. It's just you can manipulate one image, the 11 micron image. Then you can reset, and now this is where we started. Now this is the exciting button. I can look at the multi-spectral applications, so multi-channel viewer. And this will open up. And then right away I get a display that is much more interesting. This now is the same image, band 31. It tells you it's 11 microns. I have the same options down here that I had up here, with one exception, which I'll explain. So I can scroll around in here now and find out exactly where the lat lons are. And it also tells me what the brightness temperature is now. So this is quite warm, 324 degrees Kelvin in the 11 micron region. And I think it's quite hot over here. We'll come back to that region later on. The clouds are quite cold, 226. So I have a range of about 100 degrees Kelvin in this, what is called a granule. This is one granule of MODIS data. Okay, what do I have up here? Up here, I have reflection in black, and I have brightness temperatures in purple. If you remember, MODIS has several visible near-infrared channels, and then it has several infrared channels. We display the infrared channels as brightness temperatures, and the wavelength is indicated down here. Here are the 4 micron channels, and I go all the way out to 14.2 microns in my largest wavelength channel for MODIS. So here I'm sitting in a cloud. In fact, let's go back over here. In a cloud, and the brightness temperatures are quite the same. Some of these channels are in CO2 absorption, some are in water vapor absorption, but there's not much water vapor and CO2 above the cloud, so the brightness temperatures are all the same. And you'll see also that the reflectances, as I go from the visible to the near infrared, they drop off quite a bit, and you expect this. I can't see too much of the reflectance here, so what I can do is use this button here, and I can take this part of the spectrum and increase it. Now I can see the buttons as a function of wavelength much better. And you can see that I have many of my visible near-infrared channels. This is the 1.6, the 1.38, and this is the 2.3 micron channel. and I have an indication here of the reflectance from 0 to 1. All right, so I now, for every pixel that I go to, can look at the reflectance. All right, so I can go to the desert, I can go here, I can go to the water, I can go to a cloud, and I can right away see roughly what's happening with these channels. So it's a very quick visualization. And again, the same thing then for the infrared channels. I can see what's happening as I go to different locations. Over here in the very hot region, this is quite interesting. 11 micron. This is the 9.7, the ozone. This is the 8.6. This is the 7.3, 6.7, and you can see the wavelengths are marked down here. You don't have to do this by memory. This is already quite interesting because the 8.6 micron channel is less bright in temperature than the 11 micron. So you suspect that this is a region where the emissivity from the surface is less. If you remember yesterday, we showed a spectral dependence of ground emissivity, and when you were in a region without vegetation, mostly desert region, the 8.6 micron channel emissivity is less than the 11 micron channel. So you suspect right away, because the 8.6 is less than the 11, and it's not in a cloud, that you're in a region here where you have no vegetation. But we'll come back to this. This is one of the things you suspect. You can also look, and in different regions, the 8.6 might get larger than the 11 micron. So let's look for a region where this might happen, which would be an ice cloud. And let's zoom in on an ice cloud. And I suspect that this one right here might be an ice cloud. So I'm going to go here, and I'll put my marker right here. And it's hard to tell with the scale here, but the 8.6 looks like it might be a little bit bigger than the 11 micron. Not sure, but we'll come back to this also. So at any rate, you can see the whole spectrum, and you can start asking yourself some of these multispectral questions. Remembering those many, many charts that we showed yesterday of the spectral dependence from grass, from ice, from clouds, from dust. Of course, you don't remember those, so you need a piece of paper with them in front of you. Now, one thing you notice is if I go and I keep blowing up on this, this is actually quite disappointing. Jim Purdom said to me once, I thought MODIS was a 1 kilometer instrument. That doesn't look like 1 kilometer to me. Jim has looked at a lot more imagery than I have. And I said, I don't know, it looks fine to me. He said, no, that's not 1 kilometer. This was several years ago. So I went back and I said, is this 1 kilometer data? They said, yeah, but you have to display it as 1 kilometer data. So the way you display it as 1 kilometer data is you go here and you take a small piece of the granule. And now over here, it takes a while. And now when I zoom in, my good friend Jim is a lot happier. And he says, yeah, that might be 1 kilometer data. So this is one of the things that Jim taught me, that he knows more about resolution than I do. At any rate, if you look at the image now at 1 kilometer resolution, one of the prices you pay is, before I was showing it at 10 kilometers. With 1 kilometer, I have 100 times more data. So if I choose the whole granule, things slow down a lot. So I chose a small amount here, not too big, and I still can get HYDRA on my computer to work pretty well. So let's stay with this for a while, and let's look and see what we can find in this granule. I can still do the same things I did before. I can go to different locations, and my spectra changes. And now I'm able to pick out some features here that have me a little bit excited. Let's go back to color, because sometimes color can enhance things that black and white won't show us that much. And let's play with the settings. And I'm particularly interested in some of the things that are happening here. So this is over water, so I'm going to ignore some of these colder temperatures. And I'm going to come in a little bit here too. So I'm focused now just on the temperatures that I might see over water. The land temperatures are no longer as interesting. And I have regions here that seem to have things happening. Blue here, and then orange, and then yellow. One of the problems with the display in the multi-channel viewers, I can't really tell what my temperatures are right away. But I can go to something called the Transect. All right? So the Transect tool is telling me here I need to do a shift right drag. And what that does then, if I do shift right drag, gives me a chance to see what the temperatures are on this line. All right, so this is still 11 microns, and I'm going along, and I have a range here of 12 degrees, 296 to 284. My green dot is in the middle of this little feature, and I went from here to there. You have to remember which way you drag. So I look here, and I go through some very warm water. Then I have something that could be cloud, could be something, low-level moisture, but it's 12 degrees cooler. Then I go back in this feature, which is, again, it's about 294 degrees. Then I go through a cooler region again, then warm, and then this cooler region, and then finally out into the open water. But this is the feature that I have then if I look at band 31. Now, Dr. Purdom today was talking quite a bit about 4 micron and 11 micron. Let's look at this same transect now with 4 micron. And I can do that two ways. If I can't remember the channel number, I could just say, well, I'm going to take my arrow, I'm going to drag this thing over here. I want 4 microns. All right? So it's going to take a while. Think about what I just asked it to do. But there it's now channel 20, the 3.8. And you notice that the transect changed. The transect became relevant for this image. But I might want to compare the two, so I go into settings. Now I can see the last two. So now I have the transect. This is the 4 micron. This is the 11 micron. All right, the 11 micron is always a little bit cooler than the 4 micron in this image. And in some cases, the difference is quite large. So if I see a large difference like this, if it were over land, I would say that might be a fire. But over the ocean here, I'm not sure exactly what I'm looking at, but I suspect that there's a bit of reflection, solar reflection, off of low-level cloud here. So some of these features possibly are low-level cloud, where it gets a little bit cooler. Could be fog, except this is the afternoon orbit. This is from the PM orbit at 2 p.m., so I don't think it's fog. So it could possibly be just some low-level clouds. Okay, so that's the Transect tool, and you can play with different channel combinations. You can always show the last two, so you can make spectral comparisons. I'm going to get out of that for now. I'm going to go back, and I'm going to do the black and white again. And I'm interested now in going to another tool. Let's do a RGB. And we have here basically the 0.65, 0.55, and 0.45 channels. And this can give you sort of a pseudo red, green, and blue image. It takes a while because there are a lot of pixels here. But this then would be something that would be indicative of what this looks like to your eye. One of the difficulties with HYDRA is you get a lot of windows that open up, and you have to keep track of which they are. But so now if we look at this, at least in the red, green, blue, you could suspect that there's some cloud contamination in those regions. So the 4 micron minus 11 micron difference possibly again was the solar reflection or the emissivity difference out of this low-level moisture. Can't rule that out either. So you have sort of something that is familiar to the eye. So far we've demonstrated the transect and the RGB. Let's go to this reference spectrum. I'm going to turn that on. Now, reference spectrum, there's a red dot. And the red dot will usually show up at something that's extremal. Sometimes it's difficult to find the red dot, so you pull back so you can see where it is. But it's right here in the transect. So I'll go back to the normal. I'll take the red dot, and I'll pull that down so that it's nearby. In fact, let's say I want it in this feature, and then I'm going to go right next to it in that feature. And you can see that I have some spectral separation in the two, and I'm not sure what that is yet, but I'm going to play with the difference of 4 micron and 11 micron some more. I have my reference spectrum set up, and I'm going to go to the tool now that's the most powerful one, and that's linear combinations. Linear combinations allows you to take any 4 spectral bands and combine them, either addition, subtraction, division, or multiplication, or nothing. By default, it will take the 4 micron minus 11 micron, so that we can see where we have thermal emission plus reflected solar minus just thermal emission. And I can now ask it to compute an image of the difference in brightness temperatures of these two channels. I could also multiply them by different amounts. I choose not to. I just want to take the straight difference. 4 micron minus 11 micron. So now I ask it to compute this. And while it does that, I will get some water. So now I have an image, and in black and white, I have a scale here from 0.3 degrees difference to 81 degrees difference. Let's set this so the color range is more indicative of most of the pixels. I must have one pixel where it's 82 degrees, so that's a bit of a waste. I'll take that in here now, and the color difference now is going to range from 0, and this is going to be to about 35 degrees. It's indicated up here. So minus 1.4 to 35 degrees. I'm going to come in just a little bit more so I get some enhancement here. And now I'm going to look at this in color, because then we'll see exactly what's happening. The blues, almost no difference. In this region, I have something on the order of 10 degrees. Let's go back out so we get a little more contrast. And I might ask myself again, what did the transect here do? If we remember correctly, we had something like 10 degree differences. But in case I forgot, I can do another transect. I'll open this up. And now I'm doing a transect on the difference image. And there it is. And right where the green dot is, I have a difference of about 6 degrees. My maximum difference is 16 degrees in there. So I'm going to close this again. And now let's focus in on the 16 degrees and see if we can really see some small scale features. So 16 degrees would be somewhere in here. Now, everything else will look pretty lousy, but let's blow up on this one feature here. And let's see what we might have here. And let's play with it a little bit here. Got smaller. So this very much looks like low-level cloud. And in this way, we're exploring what's happening with the 4 micron minus 11 micron. Now, I have the ability to take this image and save it. And I'm going to put it over here. And now I might want to display this against something else. And here we have the thermal plus reflected. Here we have just the thermal. We should maybe look at a channel that is just the reflected. So let's go to the channel 1 and just compute that. Don't really have to compute it because I'm just asking to see the visible channel, but I need to do this in the linear combinations tool because I'm going to plot the visible data against the 4 minus 11 micron data. So let's look at this picture, set the color range, make it reasonable. And now I can see that I have visible data. There are not too many features here, but in some sense, that might be interesting. So now I'm going to put the visible data on the y-axis and the 4 micron minus 11 micron brightness temperature difference on the x-axis. And now I'm going to compute a scatter plot. So this is the scatter plot. This is a plot of all of the pixels in the visible. Let's get this back. Versus the 4 micron minus 11 micron brightness temperature difference. And these are the pixels. So now the question is, let's find out where are we in the scatter plot with respect to the images. First thing you might ask then is, what is this arm right here? This would be something where we have very big brightness temperature difference, and the reflection is modest. Reflection of 1 is a lot. Reflection of 0 is hardly any reflection. So I'm going to capture these and paint them all red in the pictures. All right, so that's somewhere right here. This happens to be in a very arid region, and it's quite hot, and that's where I have my maximum 4 minus 11 micron difference. And we'll see it over here also. So I'm going to make this picture a little bit smaller. Now we might ask also, where are all these guys? I'll paint them blue. So this is very big reflection, and also a big difference, 4 micron minus 11 micron. And that's down here. And that, I suspect, is a cloud. Our most popular pixels seem to be down here. Where are they? They're in the water. Okay, so now I might ask myself, where are these pixels in the scatter plot? So then I can go here into the image, and let's say I don't want a box, I'll draw a curve. I will take a red curve and mark it around this feature right here. And I want to see, where is that in the scatter plot? That's where these pixels are in the scatter plot. So I can go back and forth between the image and the scatter plot, and this is very useful for determining thresholds. Many of your multispectral tests involve that x minus y is less than gamma. And then you find out that gamma worked for one granule, but it doesn't work for the next granule. So getting these thresholds so they work for more than just one granule is very important. And you can test those gammas or those different thresholds in different granules in this way with the scatter plot. Okay, I'm going to see if I can show you anything else that's very clever here. And I don't think I can with respect to the 4 minus 11 micron. But I would like to now investigate what I was talking about before in terms of ice cloud. Now, we talked yesterday a little bit about the 8.6 micron channel minus the 11 micron channel. That if it's an ice cloud, that would be a positive difference. So I'm going to take the 8.6 micron channel, which I know is channel 29, and subtract the brightness temperature of that from the 11 micron channel. Okay, so I have that image right here. And that's kind of exciting. I can see that there are definitely some features. Let me make sure I'm using my dynamic range correctly. I don't need to spend too much time on that one pixel. So this is my contrast. Come in here. And now let's have the luxury of color. I go up here and I'll show this in color. So now I have, in red, I've indicated those channels with a positive value of 8.6 minus 11. And they show up in the feature that I suspected was a cloud. Okay, so this is where I think the ice clouds are in this image. Dr. Pertl mentioned today that wonderful channel for picking up high-thin cirrus, which is the 1.38. That's band 26 in MODIS. Band 26 doesn't see the surface. It only sees the upper half of the atmosphere, the upper half of the troposphere. So it's quite dark, so it definitely needs some help in setting the color range. So I'll go down here. It's not exercising very much of the range. But if you look now where band 26 is telling you where there are clouds in the upper half of the atmosphere, most likely these are going to be ice clouds. There they are. I can change the enhancement now. So I've called this an ice cloud because the 8.6 minus 11 is positive value. The positive value might not be very large. So when 8.6 minus 11 becomes a small difference, your confidence decreases. But I have differences here of 2 to 3 degrees, and I'm pretty happy with that. But just to be sure, I could take a transect through here and see what this value is, or I could just go down here and ask what that value is. It's 1.82. So I'm pretty sure this is an ice cloud. It's high enough. It also shows up in my 1.38 image as an ice cloud. Okay, I can do various other things. I'm not going to right now. I'll show you some slides of the data that I processed here. What I'd like to do now is show you some AIRS data in combination with MODIS data. All right, so I'm going to get out of this, but I am going to save this, but I'm going to do it in black and white again. Inverse gray. And I'm going to go back to my 11 micron image, because that is my best reference point. And I have my image there, and I have one set of data then. Now I'm going to go back to my main HYDRA window, and I'm going to load the AIRS data from the same time. And the AIRS data then from June 6th is coming up. This is AIRS, and this is the MODIS data. Now, because I blew up the MODIS data, I don't have as much coverage, so I will focus in on this region with the AIRS data also. Do I want to do that? No, actually I don't. I'm going to get rid of this. I'll load the MODIS data again. So here now I have AIRS data, and you'll see that the resolution on the AIRS data is quite coarse compared to MODIS. I'm going to display the MODIS data now at 10 kilometer resolution. That's why I'm loading it again. I had it at 1 kilometer resolution, and I don't have enough of the region where I have both AIRS and MODIS if I have the MODIS at 1 kilometer resolution. So now I have two multi-channel viewers. On the left-hand side is the MODIS data. On the right-hand side is the AIRS data. Let's just play with the AIRS data by itself for a while. I can do the same things I did with the MODIS data. I can zoom in, big deal. I can zoom out. I can move it around. I can show it in color. And I can change the enhancements. This is for the window channel on AIRS. So all of the things I did with MODIS, I can do with AIRS. I can also open up a reference spectrum. That's a lot of fun. So now I have a reference spectrum, and I don't know where it is unless I go back to black and white. And now let's pull back. I have to find the red dot. Oh, the red dot is right there. All right? So I'm going to go to the normal projection, and I'm going to look at the two spectra by themselves for the red dot and for the X. So I can move around here, over the water, clear sky, roughly the same. Let's pick out this little piece of cloud. The spectra all of a sudden looks quite different. The AIRS versus the cloudy versus the clear sky. And earlier we were talking how we thought this might be an ice cloud here. If you look at the spectrum, and I'll blow up the part that I'm interested in, this part right here, it's very definitely an ice cloud because the brightness temperature increases with wave number in the infrared window. When I go from 800 to 1,000, the brightness temperature increases. Whenever that happens, you can bet a lot of money that this is an ice cloud. Not all of your money, but a lot of your money. Okay, so this is an ice cloud, and I'm pretty happy for that. The other thing, we were over in this region before, and it looked quite interesting because the 8.6 minus 11 micron channel with MODIS was suggesting this could be a desert region, or at least non-vegetated. I'm going to take my arrow and I'm going to move it over here. So now my spectrum is just from this region, and I still have this red dot. Let's move the red dot over so he's not so far away. Wait, I'll leave him over there, actually. I'm quite happy for him. So the first thing you see with the spectra over here is that it's quite hot. 320 degrees, and over water it was more like 290 degrees. The other thing you notice is you have a decrease in brightness temperature. The opposite of an ice cloud, you have a decrease in brightness temperature as you increase wave number. This is very, very indicative of dust. You have dust in this field of view. The other thing that tells me for sure it's probably dust is if I look what's happening here below the ozone absorption feature, which is right here. I have 320 degrees. Then I drop off almost 10 degrees when I go to the short wavelength or long wave number side of ozone. This and this are so different. This has to be a non-vegetated region. Boom, down to here. Okay, so I am quite positive that I'm looking at a piece of China here where you have no vegetation and there's dust in the air. All right, what else do I want to do here? Let's go back and look at the clouds. Let's take a field of view right over here, over land, and let's take another field of view right next to it in a cloud. All right, so the black spectrum is in a cloud, a quite cold cloud, and the red spectrum is in clear sky not too far away. The red spectrum, just to refresh your memory, we're starting here from about 600 wave numbers and going out to 2,500 wave numbers. And in the CO2 absorption feature, as I go from the center of the feature, the vibration band, out to the edge, I see warmer and warmer temperatures. So I'm getting deeper and deeper into the atmosphere until I see surface. And my surface here is something like about, these are now 180, 200, 220, 240, 260, 280, 290, 300, 320. I'm looking at maybe something where the brightness temperature is 310 degrees. So it's quite hot. And if I look at the cloud, it's quite cold. This is going to be somewhere around 220 degrees. I go into the ozone feature. In clear sky, the ozone feature sees less deeply, and I'm going to see colder temperatures. In the cloud, I go into the ozone feature. I see less deeply. I see warmer temperatures. We have something to discuss there. And then, mostly in the cloud, there's no change in temperature. As I go into the water vapor band in clear sky, I get to colder and colder because I'm seeing less deeply into the atmosphere because of the water vapor absorption. Whereas in the cloud, there's no water vapor left above the cloud. So there's no change in brightness temperature. I'm not seeing any deeper or less deeply here. The most interesting thing is when I go, and this again is the missing airs data, I go to the short wavelength side. Look at this huge increase in temperature as I go to shorter and shorter wavelengths or higher and higher wave numbers. As I go from about 2200 to 2600 wave numbers, my brightness temperature changes from about 260 to 310. What is this? Did the cloud all of a sudden get so much hotter? Somebody help me. Who's awake?
Is this daytime or nighttime? Yes. It's not an answer, daytime or nighttime. Yes, when you drive through the one. Which is it, day or night? Everybody says daytime, raise their hand. Everybody says nighttime, raise their hand.
Nobody's awake. I won't ask you too many more questions, but this is important because we've talked about 4 micron and 11 micron for quite a while now. So This is the 4 micron region. This is the 11 micron region. So as I increase, as I go to shorter and shorter wavelengths, what's happening here? Reflectance is a very good answer. What's happening is we're getting the sunlight is bouncing off of this cloud and coming back into my radiometer, and that sunlight is in the 4 micron region. Or in wave number again, remember 2500 is 4 microns. I can fit 2500 4 micron wavelengths into 1 centimeter. So wave number and microns, it gets a while to get used to that. But this is 4 microns right here, and I'm seeing reflected solar radiation. I see even more as I go to shorter wavelengths or higher wave numbers. You only get reflected solar radiation during the daytime. So Dr. Purdom is asking you if it's nighttime or daytime. He's going to insist that this is daytime. And he's right. He's a smart fellow.
Can you put that over at cumulus field and show what it looks like on cumulus?
Well, these are the best ones I have in the granule. Where do you want me to put it?
Where's some low cloud?
Okay, we can go right here. Low cloud, still getting some reflection. Let's zoom in on this so that we make sure we're looking at what we want to. But it's reflecting also. Well, those were water clouds, these guys here. Some of these. I could go further south. You want to do these? Right here?
Go straight up in there. Keep going.
This?
Yeah, keep going. Some of that little bump.
Let's come back to this. Okay, so we have reflected solar. And we're back here on this thin cloud. Now, I'm over here. I've ignored my MODIS data horribly. It's feeling lonely, so I should come back and say hello. And if you look at the MODIS data now, the X and the red dot are in exactly the same position. The MODIS data and the AIRS data are looking at the same lat long. Let's blow this up a little bit. This is 10 kilometer resolution MODIS now. And this is going to be the 15 kilometer resolution AIRS. So there isn't that much difference between the two of them. But there is an interesting addition from MODIS. It has the Vis near IR. And if I wanted to, I could load this at 1 kilometer. I could see exactly what's happening within the 15 kilometer AIRS pixel at higher spatial resolution. I won't do that right now because it slows down the response time. But I can now ask what's happening in the Vis near IR where I don't have that information from the AIRS. Now, there was a feature that I was kind of excited about that I forgot to show you in the MODIS data, but I'll have to go back to the 1 kilometer resolution. There were low-level straight lines here that were possibly contrails, or they could have been ship tracks. I couldn't tell the difference, and I'll come back and show you that. But right now, what we're looking at is the fact that I can move around, and I see what's happening in the MODIS spectrum. That would be the purple, and I could see what's happening in the AIRS spectrum, which is the black. So I can move these around, and they track each other. If I go too far north or too far south, I will either have AIRS data and not MODIS, and MODIS data or not AIRS. They only overlap for some of it. The granules do not match exactly. And in fact, you can see I can go over here and I wouldn't have any AIRS data, but I do have MODIS data. So the east-west extent here is bigger on MODIS than it is in AIRS. Now, let's go back and investigate this desert region one more time, just so we're sure that we have what we want there. So I'm going to keep this over water. I'm going to put this back in where I say there's no vegetation. This is dust. And I'm going to look again at the 11 micron versus 8.6 micron brightness temperatures. And where I have the X, you look now, and no, it's not as convincing. It was earlier, but the 8.6, oh yes, this is the right way. I got confused. The 8.6 is less than the 11 micron. So the emissivity from the non-vegetated area in the 8.6 micron channel is showing up, and the brightness temperature is less than the 11 micron. So I'm focused right now on this part of the spectrum right up here. And you can see that the 8.6 in brightness temperature is much less than the 11 micron. I look at the air's spectrum, and indeed, it's giving me the very convincing signature that brightness temperature is decreasing with respect to wave number. And let's look at this again now for an ice cloud, thin ice cloud. Repeat the same thing. For a thin ice cloud now, it should be the other way around. The 8.6 will be bigger than the 11 micron. And I will go over here. And now I said before, when I have a positive slope here, that's very indicative of an ice cloud. Now let's zoom in again on the 8.6 minus the 11. And that would be for the purple. And 8.6 minus 11, it's not as convincing here. So let's zoom in and make sure we get the best possible pixel. What this is telling you is that two spectral bands, 8.6 and 11, are good, but they're not nearly as good as the multispectral data from AIRS. With AIRS, I can tell you right away, I know that this is an ice cloud. With MODIS, the 8.6 and 11, they're too close together. So it really only works if I have a pixel that's quite convincing. And here now, it's still not very much. But I think you can see that there's a bit of difference, probably 1 or 2 degrees between the 8.6 and the 11. So the difference is small, and it sometimes falls into the noise. But in the spectrum, there's no problem. I know this is ice cloud. I'm going to just blow up on this a little bit more and give myself the best chance. Before I was looking at 1 kilometer resolution data, and now with the 10 kilometer resolution, I may or may not have the best pixel. All right, so now there I think the 8.6 is finally a little bit bigger than the 11 micron. Took a while. Okay, now let's go back, and I'm going to move this over here. I'm going to hide the MODIS data for a while. I'm going to pull in the profiles. I also have, from the AIRS data, the profile retrievals. So I can load from local data the actual profiles that I derived from those AIRS radiances. And this was done using a empirical orthogonal function approach with a statistical data set. You start out with statistical data, and then you iterate to make sure that the profile matches the actual radiances. And this is a technique that Bill Smith and others have suggested, so we've been working on that for a while. I'm going to show this in inverse gray initially, and I'm also going to show you first just the air temperature profiles, and I want to have a reference profile on. Okay, so let's go back over here. I had this very nice situation where we were sitting in a cloud that was quite high, and we noticed that brightness temperature increased as I went into the ozone absorption region. Here's ozone, And in the clear sky, ozone brightness temperatures decrease as you go into the center of the absorption band. And here, when I'm in the cloud, they increase. One thing I know for sure, ozone is mostly in the stratosphere, so when I go into the ozone absorption band, I'm seeing higher into the atmosphere. So this is telling me as I see higher into the atmosphere, my brightness temperatures increased. All right? My brightness temperatures increased as I see higher in the atmosphere. So you must suspect here that temperatures are increasing with height. This happens in the stratosphere. So you suspect that this is a very high cloud. It's poked through the troposphere, through the tropopause, and it's in the stratosphere. So one of the things you could investigate, and I showed you a little bit of this yesterday, is where do the two spectra go different? These are weighting functions that never see the tropopause. So the red and the X, or the red and the black spectra, are identical. But they start to differ right about here. So let me scroll this over. And let me blow up on this feature. So wherever the weighting function for 885, 890, 895, roughly 895 wave numbers, wherever that peaks, that's likely the height of this cloud. I don't have that weighting function handy, but that's valuable information because you could calculate the weighting function for that. That would be indicative of where you're first beginning to see this cloud. Because as you go to higher wave numbers, which see progressively deeper into the atmosphere, they are seeing cloud, whereas the clear sky spectrum is seeing warmer and warmer temperatures. Does this make sense? Where the spectra split out is where the weighting functions are starting to see the cloud, whereas the clear sky sees deeper and deeper into the atmosphere. I see some confusion. These weighting functions keep going deeper and deeper into the atmosphere. But if you hit a cloud, they can't go any deeper because the cloud is opaque. So the brightness temperatures don't really change when you hit the cloud. Whereas in clear sky, they keep changing because they're going deeper and deeper into the atmosphere. And you're starting to see the rotational bands. Remember? We talked about vibration versus rotation. They're sitting right here. All right, let me go over here now. These are the temperature profiles. And this would be the picture that I would see for very high in the temperature profile retrieval. This is about 125 hectopascals. This is the temperature retrieval at 125 hectopascals from the air's radiances. And I don't see a cloud. There's no feature here. It's very smooth, some grains. It's colder here and warmer there, but this is obviously in the stratosphere. I can go a little bit deeper. I still don't see the cloud. A little deeper, I'm beginning to see the cloud, and now I really see the cloud. In the retrievals, I can do the same thing here in the picture. Let me go and change the wave number here. Let's start at something like 890. I can change this and just type in 890, and it will give me the picture at 890. And of course I didn't want 890, I wanted 690. Alright, now we shouldn't see the cloud, we don't. So I'm interested now, if I go to a higher wavelength, I should start seeing the cloud somewhere around here. So let me move this so that I can see in radiance space now what I saw in retrieval space. Let's go over here. So I shifted over just 9 wave numbers and I see the cloud. This is the weighting function moving down, and it starts to be low enough so that it is sensitive to the cloud. The cloud is colder than everything else around it, so that it shows up in the spectrum as well as in the picture of that at that wave number. So this is in retrieval space, and this is in the radiance space. I see the cloud. Now, I still have those retrievals for the clear sky, this is the purple line, and the retrieval in the cloudy sky. And I mentioned yesterday, below the cloud, your temperature profile is probably nonsense. But above the cloud, it's still quite indicative of what's happening in the atmosphere. And where those two retrievals separate is roughly the altitude of the cloud. And they separate at about 200 hectopascals. So, using the retrievals and the spectrum, I'm able to say something about the cloud height. I could have suspected it was quite high because I saw immediately that I was getting warmer as I went into the ozone feature. So these are some of the things that we can do with MODIS and AIRS data together. And MODIS and AIRS have been around since 2001 together. We launched MODIS 2001. So there's about 6 years of AIRS data. If you have a favorite case study over China, you can go back to the DAC and you can ask for the AIRS data. You could also ask for the MODIS data, and then you could do MODIS and AIRS visualization of some of the products that would be telling you something about the Earth's surface or about the atmosphere. I'm going to get out of the retrievals for now. No, am I? No, not yet. What I want to do now is go back to a part of the spectrum that is interesting me a fair amount. And I want to go back to an infrared window. And I'm going to look at now what I think is the most important feature in the air spectra, and that is the low-level moisture. And for low-level moisture, I'm going to spend some time around the water and around land. So I'm going to blow up on this now. And let's get one feature in the water. And let's move my red dot over to land. And I'm going to compare them. And I'm going to look in particular now at what's happening to these water vapor lines in the infrared window. If you recall from what we were talking about yesterday, each of these lines represents water vapor sensitivity. The water vapor molecule is set into rotation. So these are your rotational absorption lines. And we're interested in how much the rotational absorption of water vapor affects the brightness temperature. If the brightness temperature decreases a lot, that typically means that you saw quite a bit of water vapor, because your weighting functions here depend on how much water vapor there is. If this is the surface, this is the window, it sees right down to here. If there's a little bit of water vapor, it lifts the weighting. This is the weighting function. It lifts it up just a little bit. If there's a lot of water vapor, it lifts it up even higher. If I have a typical atmosphere, if it lifts it up even higher, this temperature difference will be bigger. If it lifts it up just a little, the temperature difference will be smaller. So if I look at the black versus the red, I would suspect that the black goes with the X, that I have a little bit of water vapor over this, whereas I have a lot of water vapor over the red dot. I also, of course, have to take into account the lapse rate. If I move from here to here, but the atmosphere is isothermal, there's no change in brightness temperature. If I move from here to here and the lapse rate is big, there's a big change in brightness temperature. So I can't totally say that the brightness temperature is due to water vapor alone. It's water vapor and the lapse rate. But there's obviously a difference here in what the water vapor is. So now over here I can go with my retrievals and ask what the water vapor profiles are doing and set up my reference profiles. And now I have the water vapor and for the red dot, the red line. And I said that there should be a lot more water vapor where the red dot is. And indeed, this is a pressure versus millimeters of water. There's a lot more water where the red dot is than where the X is. And let's look at the image of this. I'll move the red line down so it's showing me low level, relatively low level water vapor. So this would be possibly an image of what we're seeing in the retrievals, and I suspected this just by looking at the online offline. And let's blow this up a little. So this is a map now of, I show color bar on. So this is a map of the retrieval at 950 hectopascals of the relative humidity, or the moisture. And you can see that the dark blue is quite a bit drier than the light blue. Light blue over land, dark blue over water. So I have more moisture over land than I have over water. This is usually the other way around. But I saw that just from how much this was dipping down. I could also form an online-offline image if I wanted to. And let's just do that very quickly. I will go to Tools and do Linear Combinations. And I'm here at about 880 wave numbers. So I'm going to blow up on 880. I went too far, 880. I'm looking at this number here. Okay, and I need to now look at this carefully. And 920. So I'm looking at these features right around here. So I'm going to blow this up one more time. And now I'm going to move the red line so it's offline. And I'm going to find the green line. And I'm going to move that so that it's online. This is not a retrieval. Over here I already show you the retrieval. But now I'm looking at online, offline. The red minus the green. The red is offline, so it's less sensitive to water vapor. And the green is online, it's more sensitive to water vapor. And I'm going to compute the brightness temperature difference for these two channels. Okay, so now I have that over here, and I would like to compare that to this. This is the retrieval itself, and this now is what I got from online, offline. Put some color to it, set the color range. So this is pretty good. So in brightness temperature, I have a range of about 20 degrees difference in brightness temperature, and in the retrieval space, I'm looking at millimeters of moisture, and I have a range here of about 20 millimeters of moisture also. But now let's go and look exactly what's happening in this region. Oop, what happened? I clicked on the wrong thing here. So I want to blow this up. And actually I can't. Yes, I can. Here it is. So this is just online, offline, and one of the things I could do is do a transect, and now this would show me how much difference there is in the brightness temperatures going along there. And that's pretty good. I have almost 11 degree difference going from land to water in terms of online, offline. So there's a substantial water vapor gradient, low-level water vapor in the atmosphere. There's also some emissivity effects here, but as my retrievals indicate, it's a lot more moist over land than over water in this case. So these are some of the things that you can try to do with HYDRA. Let me stop playing with it in real time and show you a few more of the examples that I have. And we'll go through these slides very quickly. Obviously, you can compare the different spectral features. 11, 4 microns, we did that. Visible, 1.38. We can do scatter plots. We can look where in the scatter plot you find things in the image. And in this case, this is a different data set over China. We're displaying on the left-hand side 11 micron on the right-hand side, the visible. So you always have those rules that clouds reflect more than the ground and clouds are colder than the surface. So you can test that right away. Reflecting more and being colder, you find that there are the clouds here. They're very warm, non-reflecting parts of the land surface, and so on and so forth. You can test various theories and test thresholds. You can also go in the image itself and find out where it shows up in the scatter plot. And you can look at this now with the various spectral combinations. You can look for things that we've already talked about and make sure that's true. Here is a complicated slide, but we talked about the fact that you have different temperature sensitivities. All right? And this is something that you'll see in every image you look at. The 4 micron, we talked about it going like temperature to the 12th power in radians. This is the radiance ratio with respect to freezing. I showed you this slide yesterday. And in 4 microns, it goes like temperature to the 12th power. All right? And in 10 microns, or 11 microns, it goes more like temperature to the 4th power. So what happens now if I have a pixel where it's cold because I have a cloud, and it's also warm because I have land? I'm at a cloud edge. So part of my pixel is 300 degrees, and part of it is 220 degrees. The radiance I'm looking at, which is where I get my signal, the radiance for the 11 micron channel is going like temperature to the 4th power. So I have some cloud fraction, and it would be like temperature of the clear sky, which I'm going to say is 300 degrees, and minus the fraction that's cloudy, or I'm sorry, plus the fraction that's cloudy, which goes like 220 degrees. In one case, it's like 300 to the 4th power and 220 to the 4th power. In the other case, for the 4 micron, it's 300 to the 12th power and 220 to the 4th power, 12th power. What happens now when I change the cloud fraction? If the cloud fraction is 0, everything's 300 degrees. 4 micron, 11 micron, 300 degrees. If the cloud fraction is 1, everything is 220 degrees. All right, so if I look at total cloudiness, cloud fraction is 1, both the brightness temperature from the 4 micron and the 11 micron are 220 degrees. If the cloud fraction is 0, they're both 300 degrees. But in between, the 4 micron is going to respond with temperature to the 12th power. The 11 micron responds with temperature to the 4th power. So you can do these calculations very quickly, and you find that as I change the cloud fraction from 1 to 0.8 to 0.6 to 0.4 to 0.2, the 4 micron gets much warmer more quickly. If it sees a little bit of clear sky, it was all cloudy and now it's 20% clear, the 4 micron responds to the 300 degrees much more quickly because it's 300 degrees to the 12th power. So a little bit of cloud shows up immediately in the 11 micron. Here it's clear sky. I add a little bit of cloud, 20% cloud. The 11 micron right away says, oh, my brightness temperature went down. The 4 micron says, I don't care. So the 4 micron is less sensitive to cloud. I can go and, with HYDRA, display it with the same display. So that white is 260 degrees in this picture, and black is 320 degrees. And over here I have the 11 micron, and over here I have the 4 micron. 4 micron is also 260 degrees is white, and black is 320 degrees. I did this with HYDRA. I can barely see clouds in some region, right here for instance, near a cloud edge, whereas in the 11 micron it's definitely cloudy. This is because of Planck function. Because temperature to the 4th power versus temperature to the 12th power. So you will always see more cloud. Clouds will look bigger in the 11 micron than in the 4 micron because of the Planck function. It's temperature sensitivity. It's this very same thing also that allows you to see fires. The fire is never in the whole pixel. You rarely get a fire that's 1 kilometer by 1 kilometer. That would be a huge fire. It's typically part of that pixel. So the hot part of the pixel, the fire, will show up in the 4 micron much more than in the 11 micron. So this is something you can explore with HYDRA and the visualization. I'm blowing up now on a piece of that cloud so you can really see it. I went down here and looked at this cloud. Did exactly the same thing. 240 is white, 300 is black, 11 micron, 4 micron. Much more cloud is evident in the 11 micron. We use these functions. You should always keep them nearby so you know what spectral combinations you want to try. And this, some other ones too, but you should find websites where you get spectral sensitivity as a function of wavelength for whatever feature you're looking for. If it's chlorophyll, if it's ice, if it's vegetation. Find your right curves. We've showed you some that we know. Particle size, snow, grass, soil, chlorophyll. You have different spectral regions where you might see something. Here, for instance, you have a clue that if you have phytoplanktons at 5.55, you would have much more reflectance than at 0.45. How would I go about discovering this then? I would take 0.55 and subtract 0.45. And just to be sure, I would take the difference and divide it by the sum. So I would have a normalized phytoplankton index, and I'd look for where this is very different versus where it's roughly the same. And you would be mapping, to some extent, the phytoplankton in the water. You have to be careful with water reflectances, though, because most of your signal is atmospheric. You have to be very careful with any water determinations because the correction in the reflectance is largely going to be subtracting 95% of atmospheric signal and looking for that 5% of water signal. But anyway, that doesn't bother me. I'm brave enough to do this. I don't have to publish this. So I took here 0.55 and instead divided it by 0.45 to make an enhancement. And this is indicating to some extent the phytoplankton or maybe it's the sediment in the water. And you see again, this is a data set over China, but you have very interesting features here. And then I plotted on the other side the sea surface temperature, where I did a correction for moisture. So I took twice the 11 micron minus once the 12 micron. And that's pretty much a very crude correction for atmospheric moisture. So I'm looking at what's happening in sea surface temperature, and I see these fingers a little bit, and what's happening here in something to do with phytoplankton or sediment in the water. This is 0.55 divided by 0.45, and we know that I'm looking at something to do with phytoplankton production. I can zoom in a little bit on a different region. I thought it was going to be a zoom in there, but I can do the same thing here with rivers and water bodies. Again, this is on the left-hand side, something to do with sediment in the water or water productivity. On the right-hand side, water temperatures. Here finally I zoom in, and you can see on the coastline you have features here. This is the temperature, and this is the water productivity or water sediment content. So you're comparing different products and trying to make sense of it. I haven't done any retrievals. All I've done is taken multi-spectral combinations and used HYDRA to see what they look like. I can zoom in on rivers, and you can see on this river here, on the left-hand side, there's a lot of something in the river, and it's showing up as temperature difference in the bottom, but where a lot of something was, it didn't show up as a temperature difference. On the coastline, a lot of features. These features coming here. They could be piers or whatever, but they're features in the water. This is where local knowledge comes in. You know what's going on the coastline, and I'm guessing. SST to the left, phytoplankton to the right. So I've done this in quite a few cases. This is what it looks like from that data set I just showed you. A lot of interesting features in the water. What's going on here? I don't know. This is cloud or low-level fog, but what is this? I don't know. Very likely. If this is a river right here, there's warm water coming.
I expect that the biggest part. The water from Beijing comes through from Tianjin is around here.
Well, there's definitely a different water temperature associated with that. In this case, it would be cooler river. In June, 6th of June of this year, cooler water, river water going into this region. But these are things that are interesting. Blue is going to be colder. Temperatures are up here.
But the red area that's going out
This is warmer, but this is colder. Could be.
No, it is better. Now see it down on the, you look on that.
Yes, it's definitely cloud there. Yeah.
So the water coming out of the river is warmer.
At any rate, you can explore these things. Most important, yesterday I talked about cloud detection. You have to make sure it's clear sky. And I didn't do that. Vegetation, you can take the 0.8, subtract the 0.6, do a normalized vegetation index. 2 years ago, this is what vegetation looked like on 8th of May. And again, you have to make sure you're not in clouds. But where you have something like 0.8, you're definitely not looking at clouds. So these are vegetated regions. And then 2 years later, on June 6th, there was a lot of cloud in this scene. You can look over here. There's quite a bit of cloud, but you can see vegetation reappears in some of the same places 2 years later. This is indicative of why you would want a vegetation index on a geostationary satellite. If you're looking at a very specific area, geostationary, you can wait for clear sky. You can also do the scatter plots here. In this case, brightness temperature versus vegetation index. And you should always find that where you have vegetation, the surface temperatures are going to be cooler than where you don't have vegetation. And you can test that in a scatter plot and go around in here. Purple here, there's hardly any vegetation. The index is roughly 0, and it's quite hot, 320 degrees. That's in the non-vegetated region here. We were looking at that also in our image from June 6th. The red area, there's a lot of reflection. It's quite cool. Red area, more than likely, here is going to be a vegetated region. I'm sorry, not reflection here. This is a high vegetation index. Blue, no indication of vegetation, and it's a little bit cooler still. You're going to find that in the water. And then green, it's quite cold, and the difference between the 0.8 and the 0.6 reflectances is small, so that's going to occur in the clouds. So the scatter plots are a way of testing some of these multispectral tests that you think you can use. Here, this is on the June 6th case. I looked over a river and away from the river, and I tried to find out what was happening in vegetation versus brightness temperature. And you can see in the river itself, you have a range of vegetation. This is the river valley, and the brightness temperatures aren't changing that much, but the reflectances are. Whereas in the area away from the river, where I think it's quite dry, you have very little vegetation and very hot temperatures. So this is not vegetated. It's away from the river valley. It's probably barren. Whereas here in the river valley itself, you can look at it here, then you're going to have some growth near the water source. At 1 kilometer resolution, you can play around with different regions of China and find out what's happening on clear sky days. With ice clouds, we did quite a bit with that, but you can use your threshold techniques, 8.6 minus 11, and map out where you have ice versus water cloud. If 8.6 is minus 11 is negative, it's water typically, and where it's positive, it's ice, assuming that you don't have other things happening. So you have to be careful with that test, but the red here is an ice cloud, the blue is a water cloud. I'm going to continue through this very quickly. This is kind of interesting. If you plot 8.6 minus 11 versus 11 minus 12, so on the y-axis here, I have the brightness temperature 8.6 minus 11, and then I have 11 minus 12 on the x-axis, and you get a scatter plot typically like this. I'm in a cloud here. This is all cloudy region, and then as I go away from it, it's clear sky. So what I've asked myself, what happens if I go around this? What's happening? this is likely going to be -2. This should be somewhere near the edge of the cloud, and I work my way into the middle of the cloud as I get into here. So I'm progressively going from here, from the edge of the cloud, closer to the cloud, in the middle of the cloud, very much in the middle of the cloud, and when these differences are back down here to 0, I'm back on the edge. This is due to the fact that we have different temperature sensitivities. You have the 11 micron, the 12 micron, the 8.6 micron. The radiance is going like temperature to a different power. So the fact that this goes around here in a spiral for different cloud amounts is exactly what I showed you for 4 minus 11 micron. We're looking at exactly the same phenomenon here for 11, 12, and 8.6. Enough with clouds. This is a tropical cyclone. I don't remember what day it is, but you can look at the imagery and figure out what parts of the tropical cyclone has very high clouds. And these are the websites. Now, the last thing I want to do is show you just a little bit of Iasi data, because in the data set that I gave to Lufan, there is Iasi data. And with the Iasi data, you have the beautiful full spectrum. And you can look online, offline, as I did with the AIRS data. And you can start exploring where you have low-level moisture. And you can look at the ice clouds with the Iasi data. And you can also look at both sides of the water vapor absorption band. And then you can blow up the spectrum. And here you're looking at 2 pixels in the ocean and over land. And you can see that the red line and the black line have a different sensitivity to moisture. And just before we break for lunch, then we'll have one more quiz. The black line, as I go online to offline, offline being the warmer brightness temperature, has an excursion of so many degrees. The red line has an excursion of more degrees. Which one of these is more moist? The black or the red? The wave numbers are right here. You're in the middle of the water vapor absorption region. So neither of these is seeing the surface. This is not low-level moisture. But I'm going into the rotational bands in the middle of the water vapor vibrational band. So the red is going in the middle rotation. This is online, offline. So this is sensitive. The weighting functions are high in the atmosphere. But remember yesterday I showed you the differences are 20 to 30 degrees whether you're online or offline in the water vapor. The fact that this is going through a bigger excursion, what does that tell me? Well, maybe we'll come back after lunch and answer this. Yes, it is. So we should think about this. The bigger the temperature excursion, I have the wrong answer here. That's why I'm asking the question again. We'll come back to this. If you move more in brightness temperature, does that mean more or less upper moisture? That's the question for lunch. Let me see if there's anything else interesting I want to show you. No. Let me stop with the following conclusion again, that there's an awful lot of information here. I think I asked more questions today of myself and of you than I have answers. And this is good because we haven't fully explored all the information that's available in these spectra. The thing to do now is look at as much data as you can in your area of interest, in your subject of interest. Ask questions. And most of the people near you, including me, won't have the answers. Eventually you will have to develop your own answers. But that's the excitement. In this data, there's so much information, and we have to learn how to pull it out.
Can you go back to that one?
not yet. I'm giving my conclusions. HYDRA is one visualization tool. There are many. You could use ENVI, you could use other things. You would have to adapt ENVI so they could look at the multispectral data from these instruments. HYDRA happens to be the one I'm most familiar with. As I say, the optimum use of these measurements is still pending. In numerical weather prediction, we're using a very small part of the spectrum, and we're not using any of the data over land. So we still have a long ways to go before we can assimilate the information in numerical weather predictions or in head interpretation, what I can see with my brain and my eyes. So we're still working on that. But I said yesterday to Professor Xu Zhimin that I was so happy when I walked into this room because there are many young people here. And my last conclusion is many young eyes studying the data will bring us closer to using the full information content. So I leave it to you to teach me a year from now what you learned with HYDRA data from MODIS and AIRS and Iasi over China. So thank you.